All right, so just like Morgan, when I got this email to speak today, I wasn't given much instruction about what to talk about, so similarly I came up with, I want to talk about everything, because I love everything about astronomy. I took this in a slightly different direction than Morgan did, because what I was really interested in, as I've been studying astronomy for years, was how did we get to where we are today? Because a lot of the knowledge that we have about space and astronomy and everything in the universe, these discoveries happened so long ago that nowadays it seems like pretty common knowledge. But it wasn't always so. And how did we get from where we used to be hundreds or thousands of years ago to our present day knowledge of astronomy? So that's what I want to talk to you about today. Now, I really like this particular comic from this website, PhD Comics, because it sort of shows how the scope of an individual person's knowledge changes over time. You know, you start in elementary school or in high school, and you know just a little bit about everything. You know, you get a pretty well-rounded education, and as you go and you have more and more studies, and you go to grad school or you specialize in your job, you start to know a really great deal of stuff about one very tiny little part of the entirety of human knowledge. And that's sort of how astronomers and scientists operate today, is they take their very specific knowledge about a very specific part of the universe, and they use it to chip away at the answers to very large problems. That's how most science is done today. And if you want a really large result that fundamentally changes how you look at the universe, you usually need a very large collaboration that has a lot of money and a lot of time and a lot of very powerful telescopes in order to really change how we think about our place in the universe. But now, that wasn't always the case. Certainly we've heard back, in the 1800s, 1700s, individual scientists were able to make fundamental discoveries about the universe, and we credit them to one particular person, such as Galileo or Copernicus or Kepler. These are very familiar names now in today's society. And we usually think about these large discoveries as having taken place long ago. But there were actually a few very important recent paradigm changes. This isn't a thing of the past anymore. And we talk about these sort of like we talk about black swans. Back in the 1800s in Europe, they only knew about white swans. They've only seen white swans in the entire history of Europe, so white swans are the only things that exist, right? Well, that was true until they found a black swan, of course. And they used to joke about this before they found that black swan. They'd say that, this discovery is just as likely as having a black swan in a field of white swans. It's not how the world works. Well, black swans obviously do exist, and so we talk about these sort of paradigm-altering things as black swan events. Things that fundamentally change how you look at the world. I sort of like to think of it instead in terms of Bugs Bunny, because I'm a Looney Tunes girl. And if you recall from watching any Bugs Bunny cartoons, there's always a few where Bugs is traveling somewhere he's never been before, and he makes a right turn instead of a left turn, and he ends up somewhere he never expected to be. But it always turns out to be a really interesting and exciting place where lots of adventures happen. So this is where my inspiration for my talk comes from, is we really should have taken that left turn at Albuquerque. And we go somewhere we were completely not intending to go, but it's pretty exciting stuff. So I first want to pay homage to a few of the classics, because there are a few of these classic left turns that have happened in our understanding of the universe. A lot of these you may have heard of if you've ever taken an astronomy course or a general science course, or even if you've watched either the older or the more recent versions of Cosmos. We like to highlight these a lot. Firstly, I'm going to, of course, pay homage to the heliocentric view of the universe, of the solar system, which got a lot of people in a lot of trouble a while ago, which is partly why it's one of the more famous events that has ever happened. Before this, there was the knowledge, the common understanding that the Earth was the center of the solar system and things expanded outwards. You know, we had Mercury and the Moon and Saturn, and Morgan talked about all of this, of course, but it was common knowledge that the Earth was the center until it wasn't. And we used the heliocentric view, where the sun is at the center, to accurately predict where the planets would be and how the planets are moving throughout the sky. And since then, we have, of course, taken this fundamental knowledge that we're not the center of anything, and we've expanded that from the solar system to we're not the center of the Milky Way to we're not the center of the universe. And we've discovered billions and billions of galaxies that at first glance may appear to be positioned in such a way that we are the center, but we've come to realize it's just a matter of perspective. As if we had grown up in, this random galaxy right there, they would view themselves as the center. And so we learned that we can look at the universe from a variety of different perspectives, as long as we remember that we are not the center. So I'm calling that paradigm shift number 1. There was, of course, after that, the invention of the telescope. And this invention of the telescope by Hans Lippershey was really what started us on the path towards discovery. Because before that, we could only observe things with our eyes in a very dark sky, and you were limited to what you could see with your eyes in a very dark sky, until a very clever man was able to figure out how to manipulate the light and magnify it using clever shapes of glass. And when Galileo first pointed it at the sky, he was able to see many times more than we ever knew possible. And today this has brought us to the fact that we have telescopes all over the world that can look at every wavelength of light you could ever possibly imagine. We have telescopes on the ground, we have telescopes in space, we have a telescope on a 747 jet. And because of that first observation with a telescope many years ago, we have now greatly expanded our knowledge of our solar system, our universe, and our place within it. I want to point out another very important left turn that's happened that you may not be quite as familiar with. And that is when Hubble first connected the existence of the beautiful Crab Nebula to an event that happened many centuries ago that was recorded by Chinese astronomers. And that was the great supernova of 1054. Now, when Hubble first realized that the Crab Nebula's history could be tracked backwards to an event that humans observed, he first realized that the stars that we see in our sky, they evolve, and they can sometimes evolve on a human time scale. And we can see the evolution of these stars from when they were burning hydrogen and helium in their cores to when they reach the end of their lives as supernova, and the impact that they leave behind them in the universe. This was the first time that we had ever connected a supernova to a supernova remnant. This was the first time we had ever connected, we'd ever gone backwards in time and been able to connect an observation that we see today to a historical event that happened many years ago. This is also one of the most prominent ties between Western astronomy and Eastern astronomy. So I would say this is certainly worthy of a whole few slides of its own. And then even a few decades later, we learned even more about the Crab Nebula and even more about how stars evolve and change over their lifetime when we discovered a pulsar in the center of the Crab Nebula. So now we've all of a sudden, over the course of a few centuries, connected the beginning of a star all the way to its very end product. And that's truly remarkable. Now, of course, the Crab Nebula, we've also revolutionized things like plasma physics, being able to study the evolution of this very hot nebulous gas over a long period of time, stellar evolution, of course, historical astronomy. The wealth of information the Crab Nebula has given us is way beyond a 45-minute talk that I could give here. But I do want to pay homage to it because it is certainly one of the most important connections we've ever made in the history of astronomy. But again, these are things that have happened a while ago. Now, and I sort of like to think of it as, in astronomy, we sort of think that a lot of these big discoveries have already happened. And now, like I said, we're sort of just chipping away at the tiny little details to refine our knowledge of how the universe works. But there are a few very important developments that have happened in the past century and a half. The first one I want to talk about is when we learned that we could observe the individual elements and the individual components of light that make up the entirety of the universe, all of our stars and galaxies that are so far away. And that is called spectroscopy, when we first figured out that we could separate the light into its individual components and then apply that to the things we see in the sky. So the first spectroscope was created in the early 1800s. I have shown here sort of a characteristic example, a very famous one that was built by Kirchhoff and Bunsen. You can see here, they have a famous Bunsen burner and everything. And they were able to heat up elemental gases, helium or neon, things like that, and they heated them up. They pushed the light through a prism in the middle, and they observed what are called emission lines. They found out that certain elements, when you heat them up, they only glow at very specific frequencies. And so that was the first time we were able to guess that we could tie the observed light from the universe to the individual elements that they were made of. A few years later, Fraunhofer did a similar thing, except he did it in reverse. He took a spectroscope, he looked at the sun, and he instead saw absorption lines, these very dark bands that happen in the solar spectrum. And by tying together what we learned from the first spectroscopic experiments to what we see in the sun, we learned that the sun is made up of very similar things to what we see on Earth. We see things like calcium and iron and sodium and hydrogen and hundreds more of these lines. Now, there are always a few oddballs here that sort of contaminate what you're looking at. Fraunhofer was not able to figure out what these two lines were. And it wasn't until many years later that we figured out that this is actually a component of the Earth's atmosphere that was getting in the way. So we start to observe the limitations of just looking at from the ground up into the heavens. Because of course, to go from the ground to look at the sun, you first have to go through the Earth's atmosphere. And if you're looking in such fine detail, there is going to be inevitably some sort of contamination. This is a problem we're still struggling with today as to how can we adequately model what the Earth's atmosphere is doing. But it also highlighted the importance of going into space and looking through space telescopes for some particular problems. Now, this is a person I really wanted to highlight because Cecilia Payne-Kopachkin, if you've never heard her name before, you should write it down, mark it, remember it, because her PhD dissertation has been called the most influential piece of writing in all of astronomy. I happen to agree with whoever said that, and it wasn't me first, I promise, because her work was the first time we ever realized that the sun is made up of mostly hydrogen and helium, but it was also made up of the exact same material that we find on Earth. Now, you may say, oh, well, Fraunhofer found that first. And you know what he did? He found that there's iron, and there's calcium, and there's sodium, but Cecilia Payne-Kapotchkin found that not only are the same elements present, but in the exact same ratios as we see on Earth. So the sun is quite literally Earth stuff, the same way that we are star stuff. So here's a representation of what I've just said, that the ratios of individual elements, such as the amount of oxygen compared to carbon, the amount of iron compared to niobium, whichever ratio of elements you could possibly think of, they're exactly the same as we observe here on Earth, where we can pick up a rock and take it back to our laboratory and break it up into its little parts. If we look at the sun, we can see the exact same thing. This was the first piece of evidence that stars and planets form from the exact same place and the exact same material before they somehow magically turn into a star or a planet or an asteroid or whatever. They start from the exact same material, and this was the first piece of evidence we had. Nowadays, of course, we've come to accept this as part of our everyday life, that the entire solar system formed together. We come to accept that the sun is mostly hydrogen and mostly helium. These are things that are accepted as part of everyday astronomy that we perhaps learn in our first week of astronomy courses we ever take. But we didn't always know that. Her same dissertation was also the first time we were ever able to connect the differences we see between different types of stars to an actual physical meaning. And this, in particular, kick-started the entire field of astrophysics, combining the observed astronomy that we see with the fundamental physics. So this is the creation of an entire field of science that never before existed. She was able to show that the strength of these absorption lines that were observed, even as far back as Fraunhofer and earlier, those are actually completely due to the temperature differences between the stars. If you tie that to how the temperature impacts what kinds of elements you're looking at, whether it's an ionized version or an excited version, or all these little tiny little differences between different atoms, you can replicate these differences just based on temperature. And because we knew that, we were able to then take all of the stars that we knew and put them in a sequence from hot to cold, tie them to the observed properties, and we learned that the somewhat random system that we had classified them with before, with letters such as M and K and B and whatever, though that random system wasn't right. It was completely out of order. And they may have grouped certain stars together, but they didn't know where it all fit in the grand scheme of things. But Cecilia Payne-Kapotchkin showed that that sequence really should be sorted based on temperature. So that's why if you ever hear you have to learn an acronym OBAFGKM, the sequence of stars, that's why it's out of order and all mixed up. It's because we tried to classify them before we really knew why they were different. And nowadays, of course, this is one of my favorite pictures. This is the same solar spectrum we saw before that Fraunhofer used to identify elemental lines. And now, of course, we see thousands and thousands of lines in the sun. And we are able to identify where each of those lines comes from. And we're able to pinpoint what the sun is made of, what other stars are made of, what stars in other galaxies are made of. And this is something that we've never been able to do without Cecilia Payne-Kapotchkin's work. Now, if you go even farther than just learning what things are made of, knowing exactly why certain features you observe in a star or a galaxy, why they're there, you can then figure out why they don't look like they should. The usual answer to that is because the stuff is moving and that line isn't where it's supposed to be. And we call that the radial velocity method. So I would say that's probably one of the more recent things that has come out of our understanding of stellar physics, is learning how things are moving in the galaxy and the universe and everything. So that includes looking at the scope of the universe. This is the cosmic microwave background. And we can use the radial velocity method that comes out of our understanding of stellar physics to track the expansion of the universe over its entire history. We can use that same method to figure out where everything is placed in the universe. Where is every galaxy that we can see? So we get an idea of the structure of the universe. And something I particularly enjoy, because this is what I work on, is that we can use the same thing the same method to detect planets around other stars. So if we go back to, sort of the smaller scope of it, we're looking at individual worlds around other stars because of our understanding of stellar physics now. So I would say that's a pretty influential PhD dissertation that I could never hope to match in a million years. I don't think that my PhD will spawn off an entire new branch of astronomy, unless I was really lucky. So I've been talking about where things are in the universe and the expansion of the universe, but we didn't always know that the universe was wide and vast and contained all of these billions of galaxies. So I would say that the point in time when we realized that many galaxies exist beyond the Milky Way has led to a fundamental change in how we understand our place in the universe. So the time when we realized this and we came to accept it was the 1920s. And there were really two sides of the coin there. Is that there was one side who said that the Milky Way is the entirety of the universe. And everything we see out there in the wide world, that's all contained within the Milky Way. All of these spiral nebulae that we now understand are separate galaxies unto themselves, no, those would be much too far away. We can't have that. And there were multiple lines of evidence, of course, to support this, including the fact that at the Pinwheel spiral nebula, of course, someone said that they saw that spiral nebula rotating on a human time scale. And if that were really a very far away galaxy, it would be going faster than the speed of light, and that's not possible. There's the other side of the debate, of course, which is that the Milky Way is just one of many island universes. That's one of my favorite terms in astronomy, is island universe, because we really come to understand there's so much in our galaxy. It's a universe unto itself. But the side that Curtis was on also had multiple lines of very convincing evidence that things like the Andromeda galaxy were actually placed many billions of light years outside of the Milky Way. It has very similar things, features like dust lanes and novae, just like the Milky Way does. And that it's okay that the Andromeda galaxy is so far away and the Pinwheel galaxy is so far away. There's nothing wrong with that. And that's what Curtis says. And now, of course, we've come to realize that Curtis was indeed right. But before that, we had no idea. One of the very convincing pieces of evidence that the Milky Way was just one of many island universes was the work of Edwin Hubble. Now, some of you may be familiar with a term called Hubble's law, which says that the farther away a galaxy is from us, the faster it is moving away from us. So Hubble uses the radial velocity method, and here we come back to all of this again, to show that a number of the galaxies that he observed in the universe are indeed moving way too far away, or way too fast away from us to be contained within the Milky Way. There you go. Well, it was first quantified by Georges Lemaitre a few years earlier than Hubble claimed credit for it. But Georges Lemaitre fell into a very, very sad trap of publishing his work in a not very well-known journal in French. So instead, we credit Hubble's law to Hubble because he had the fortune to publish in a very prominent journal in English so that everyone could read it. But Hubble showed that the universe not only existed beyond the Milky Way, that it was very large and very vast and had many, many things in it, but it was also expanding. It wasn't just a static universe, which also went greatly beyond the established thinking of the day. That the universe, even though stuff within the Milky Way might be changing over time, the universe outside of us was static until Hubble proved that wrong. So if the universe is expanding and a bunch of stuff exists outside of the Milky Way, what else could be out there? Now, Fritz Zwicky had a very interesting idea back in the 30s. He was looking at the Coma galaxy cluster, which is a very large structure that contains hundreds of galaxies just like the Milky Way. And he was looking at it, and he said, these galaxies are moving really fast relative to each other. The only way they could be moving really fast is if there is a lot of gravity that is moving them around. And when you calculate all of the gravity that should be there, just when you look at all of the stuff that is shining, all the stars and gas and things you can observe with your telescope, if you estimate how much gravity there should be compared to how much gravity there really is, you fall way short. So Fritz Zwicky says there must be a great amount of stuff producing gravity that we just can't see. And he was the first one to call this dark matter. Of course, he said it in German and not in English, but it translates to dark matter anyway. A few decades later, another influential woman named Ruth Rubin came up with probably the most definitive argument that dark matter has to exist by looking not at the movements of whole galaxies relative to each other, but by looking at the motions of stars within those galaxies. And using a very similar line of reasoning, she says that the stars within a galaxy that is rotating, they're moving much too fast to be held in place by just the stuff we can see. There must be more stuff that we can't see holding it in place. So this is how we've come to understand that there is quite a large amount of dark matter that exists in the universe, both on the scope of an individual galaxy and the scope of hundreds of thousands of galaxies. This is something that permeates the entire universe, and we've now come to accept that. Mostly. In terms of what else is in the universe, Einstein has his famous blunder, as he called it, which is the existence of a cosmological constant. So if we go back into the past a little bit, before Hubble showed that the universe was expanding, it was common knowledge that the universe was static. It wasn't moving at all. And so when Einstein applied his theory of general relativity to the universe, he came up with something that was expanding and said, that can't be right. And so he added a constant term to his equations to counterbalance the expansion that general relativity predicted in order to keep things nice and stable. A few years after that, Edwin Hubble showed the universe was expanding, as we saw, and Einstein went, and said that he was wrong, and he redacted it, and he took away the cosmological constant so that the universe was expanding and his equations were correct again. Then, quite a few years later, in the 90s, so now we're going all the way to the end of the 20th century, we learned that the universe is not only expanding, but it is accelerating. The expansion is going faster and faster and faster, And so even though general relativity says, yes, the universe should be expanding, it needs to be expanding faster. And so now we've added the cosmological constant back in. So Einstein is sort of redeemed in this case. He was right after all, just not for the reasons he thought. So now we have our understanding, and you may have seen this before, is that the universe is 70% dark energy, this force that is somehow making our universe expand faster and faster, this acceleration we see. There is a large chunk of dark matter which is causing the smaller scale motions of galaxies and stars to be faster than they should be, and that less than 5% of the entirety of the universe is normal stuff. Everything that makes up stars and planets and beautiful supernova remnants and nebulae, that's less than 5% of the universe. And even if we just look at this, if we look at the stuff that makes planets, anything heavier than hydrogen and helium, really, everything that you and I are made of, that is 3/10,000ths of the universe. An incredibly minuscule amount has created everything in our world, all the other planets, any other planet we could ever possibly find. So imagine what you could do if you could work with all of this. That's what I like to think. Another sort of groundbreaking thing that I want to mention, sort of fun, is the discovery of the surface of first light in the universe, called the cosmic microwave background. It was discovered quite on accident, completely not intentional, by two guys named Penzias and Wilson who were over at Bell Laboratories. They weren't looking for it. They didn't want it there. But when they were measuring, they kept seeing this fuzzy stuff that showed up in their radio telescopes. They were very, very confused. They could not, for the life of them, explain it away. They even went so far as to climb up into their telescopes and give it a really good scrub down, trying to get rid of whatever was causing the fuzziness. And it was still there. And they eventually realized that this was the same sort of radiation that the folks down the road at Princeton had predicted would be there. And so Penzias and Wilson, in a very famous paper, published, and they said, we've discovered this relic radiation of the universe, this relic heat left over from the creation of the universe, the cosmic microwave background. And so these people who weren't even looking for it ended up sort of scooping the discovery out of the hands of the folks at Princeton who were looking for it at the same time, but just weren't quite quick enough on the draw. This resulted in a Nobel Prize in 1978. I think it's one of the most, the funniest sort of story in astronomy, I would say, that discoveries come from the place you would least expect them. We've taken a very close look at the cosmic microwave background over the course from when we discovered it to now. We've sent up many satellites to look at it in great detail. And what's really remarkable about it is that it not only is a very sort of like hitting the nail on the head in terms of predicting the Big Bang and what would result from it, but if you look at all these tiny little dots, each of these represents a measurement of temperature in the universe, where red is hotter than blue. And if you compare the structure of the universe in terms of where all of the galaxies and everything fall to this map, this heat map, you could call it, of the universe, is that every place where there is a hot spot, there is a galaxy. Where there are cold spots, there are voids, completely bereft of galaxies and stuff. So you can go all the way back to the Big Bang, look at the very first light of the universe, and if you map it forward, you can predict where everything should be 14 billion years in the future. So if anyone ever asks you why most people believe the Big Bang is really real, this is your answer right here. But we would never have known that if we we didn't first understand that there's an entire universe that existed outside of the Milky Way and that we were nowhere near the center of it. We just had to sort of expand our minds that way. So now we come to probably the most recent left turn, the most recent black swan that has happened in astronomy, and that is the discovery of worlds that exist outside of our own solar system. Now certainly if we hadn't done that, I would not be here talking to you today, because this is why I study astronomy, is my fascination with worlds outside of the solar system. And our understanding of planets has certainly greatly changed since the 1500s. From our geocentric model of the solar system with the Earth at the center, to our heliocentric, correct view of the solar system, to the discovery of Uranus, the discovery of Neptune, the discovery of Pluto. This is not what Pluto looked like when we discovered it, mind you. This was only a few months ago. We discovered Pluto, we got rid of Pluto, sad times. And then we discovered the first world around another star. Nowadays, we know of many, many worlds that exist outside of our solar system. Now these numbers were taken just a few days ago. 1,900 confirmed planets that exist in just that tiny little portion of the sky that Morgan showed earlier. Nearly 5,000 more planets that we could confirm if we just had enough manpower. We're getting to them slowly but surely. And that nearly 500 of those planets exist in systems that have more than one planet, just like our solar system does. Some of these have 5, 6, 7 planets that orbit the same star, that could potentially look just like our solar system or have very similar planets to what we see in our solar system. But if you ask anyone which one came first, there's a problem there. It's a bit more complicated than you would first believe, because when you look at the first few planets that were ever discovered or published or detected, you run up with a few issues. You have some that were detected first, but were not claimed to be planets. No one wanted to be first, to say it was a planet and then be wrong. You have some planets that were definitively published as planets right off the gate, but they exist around an object that is not a star. It's a stellar remnant. It's something that used to be a star. But are those still planets? We don't know. And then you get to probably the most conservative estimate of when the first planet was discovered, the classical 51 Pegasi, which was published first as a planet around a sun-like star, and it happened pretty early on. So if we look at each of these candidates, we can we can weigh which one is most likely, which one should get the credit. Now, the first one that was technically published, the first one that was technically measured, is Gamma Cephei B. It was discovered via radial velocity. It's one of the most common methods in astronomy. But it was published as a substellar companion, or something like a brown dwarf, that is a failed star. And it wasn't until 2003 that we learned that it was actually a planet with a mass just a little bit more than Jupiter. That's not a bad type of planet, but it wasn't until 2003 that we had confirmation that they were right. If you go to our second candidate, which is HD with a telephone number after it, you can never remember the numbers, you're in a very similar situation. You have a planet that was discovered, that was not published as a planet, but it was confirmed very early on, even before the other the third and fourth candidates that we have. It was confirmed really soon after they published first, but should you reward someone for saying that it wasn't a planet and then changing their mind? This particular system of planets is one that is close to my heart because it was discovered by an astronomer at my graduate institution at Penn State. These are a system of 3 planets that were discovered around an object that's not a star. It's a pulsar, which is what a high mass star will become after it dies. Now these planets, they're incredibly small. 2 of them are only a few times more massive than the Earth. One of them is only twice the mass of the Moon. It is still, to this day, one of the smallest planets that we have ever found. But were these planets formed? Did they exist at the beginning of that solar system's life? Or did they perhaps form out of the debris that happened when that star went supernova? Are these original planets in that system, or are they sort of the second generation of planets? Is something that is a second generation planet still a planet? Is something that is not around a star still a planet? We still don't have an answer to those questions, by the way. In 51 Pegasi b, again, sort of the classical first planet that you look at was indeed a planet, published as a planet. They knew it was a planet right out the gates. It's around a sun-like star, something that is still burning hydrogen in its core. But it was something that they'd never expected to see. It was a Jupiter-sized planet, but it was incredibly close to its star. It orbits in only 3 days. 3 days. And we had no idea that a planet could even exist that close to its star. It's very strange. We now know that these types of planets are actually more common than you would expect. These are one of the more common types of planets. They're called hot Jupiters. Jupiters because they are Jupiter-sized, and hot because they are really close to their star. Really close. But it was something that we had never expected to see. So if you ask most astronomers which came first, most of them will say either 51 Peg, because it is the least controversial planet you could pick, essentially. Others will say the pulsar planets, because they were indeed confirmed first, before 51 Peg. But until astronomers actually make up their mind as to what is a planet and which one came first, you will see no Nobel Prize for exoplanets. So I'm really hoping that they figure that out soon. After the first few planets were discovered, though, sort of like the floodgates were open. We discovered planets dozens at a time, mostly using the radial velocity method. So everything shown in red here was detected using radial velocities. If you count every other method that you could use to detect a planet, they didn't detect all that many until sort of the mid-2000s. You start getting more and more transiting planets when we started launching telescopes like the Corot mission or the WASP mission. We started learning that we could detect planets even more easily using the transit method, and we could do them dozens at a time. But of course, I want to highlight my favorite telescope in the history of telescopes, which is the Kepler Telescope. And this is why we keep talking about it. Is because if you look at all the planets discovered before Kepler, and then the first chance we got to look at the entirety of the Kepler data set, it literally changed the entire scale of exoplanet science. So if you recall, here is the maximum we had before. It was a few hundred at most. And now, of course, we have 1,900. Most of those came from the Kepler Telescope discoveries. Not only did it find so many exoplanets, but it found planets that we just don't see in our solar system. And they found that the types of planets that are most common in the universe are ones we just don't have. Things that are between the size of the Earth and the size of Neptune. In our solar system, we just jump from Earth to Neptune in size scale. But most planets fall right in the middle. So why don't we have one? Why don't we have a hot Jupiter? Why don't we have an ocean planet? These things that we see out in the universe are starting to tell us that maybe our solar system isn't normal. Maybe we're the weird ones. And of course, Kepler, if you look before Kepler and after Kepler, and you're looking at where we're finding planets and how big they are, Kepler has certainly pushed the boundaries of the types of planets we can detect, the types of planets we can learn about. And we're going to keep pushing this boundary until, and hopefully past the time, that we find another world that looks just like our own. So, where do we go from here? Now, we say that most of the large discoveries in astronomy have happened years ago. But there are clearly some that have happened in the past century that have spawned entire new branches of science, and entire new fields of physics have, made us make even bigger telescopes and learn that our universe is incredibly vast and ever-changing. So what is there left to do? What can we look forward to in the future? The answer is quite a lot. I've just picked a few that I still think are really interesting, large, unsolved questions that we have about the universe, such as, what is dark energy? Is there life outside of the Earth? What is dark matter made of? Where did all the antimatter go? These are some still rather large questions that would explain the unexplainable that we see in the universe. Now, I'm sure that there are even more than just these 6 that I've written down that we possibly can't even think of yet, because we're not in a place to realize that these questions exist. But one thing is definitely for sure: the universe is incredibly wide, incredibly vast, and an incredibly mysterious place, even still. So, thank you.